Hello, everyone. By far, we have learned that many classical causal inference methods have been proposed to deal with the challenging issues of selection bias and missing counterfactors. In recent years, we have been trying to address the same issues from the perspective of machine learning. And in this section, I want to introduce some subspace learning methods for causal inference. At the beginning, I want to briefly talk about why machine learning is helpful for causal inference. We know that machine learning covers a lot of learning tasks, such as regression, classification, and clustering. And it can also be used in various settings, such as multi-view learning, multitask learning, transfer learning, and so on. And more importantly, many machine learning models have the capability of learning compact and informative features from high-dimensional input data. Overall, we believe that machine learning models provide with us many useful tools to discover insights from high-dimensional data, which will be helpful for causal inference. In particular, we have identified some connections between causal inference and machine learning. First, matching is a traditional approach for causal inference. However, traditional matching estimators are usually performed in the original feature space, which might not be effective. If we use machine learning to learn a new representation space, the matching estimators could be further improved. Second, covariate shift is a common problem in machine learning models because of the different distributions of training data and test data. Actually, this issue is quite similar to selection bias in causal inference because the treated group and control group may also have different data distributions. Therefore, it's possible to leverage some ideas from machine learning to do the group balancing. Next, in causal inference, the major issue is to infer the missing counterfactors. And this problem can be modeled as a regression problem by considering the input as the covariates and the counterfactor as the outcome. Now we can have a quick review of the subspace learning. The goal of subspace learning is to learn low-dimensional subspaces for dimensionality reduction. There are many subspace learning methods in machine learning field. Some traditional ones include PCA, LPP, CCA, and many others. In this figure, you can see the idea of PCA. Given a number of data points from the 3D data space, PCA will find the two principal components and map the data to a 2D space. In this way, the dimensionality of data could be reduced. Our motivation of using subspace learning for causal inference is that matching in the original data space is simple and flexible, but it could be misled by variables that do not affect the outcome. To address this issue, matching could be performed in the subspaces instead. There are some methods in this category. We will introduce 4 of them, including random subspace-based method, informative subspace method, the balanced and nonlinear subspace-based method, and also our most recent work on selective and balanced feature space. Before going into the details of this method, we need to first review the idea of nearest neighbor matching, which is a traditional matching estimator. The idea is that for a treated unit I, the nearest neighbor matching will find its nearest neighbor in the control group in terms of the covariates, and also a predefined distance metric. Then we can use the outcome of this neighbor as the estimation of counterfactor outcome. Some examples of distance metrics used by nearest neighbor matching include the Euclidean distance and the Mahalanobis distance. If we only have a few covariates, this method is very effective. However, it has difficulty in dealing with a large number of covariates. In particular, some theoretical analysis shows that the bias of nearest neighbor matching will increase with the dimensionality of data at a rate of big O of n to minus 1 over d. Here, d is the dimensionality of data. So this theoretical result motivates us to reduce the dimension of data. And our first work on this topic is by using random subspaces, we can improve the performance of nearest neighbor matching. Our motivation are twofold. First, we want to reduce dimension of data to soften the dependence of bias to dimension. Second, we want to do linear projection so that the model will be very efficient in terms of dealing with big data. The key in nearest neighbor matching is to find the neighbors for the units in treated group. So we assume that if we can find such a subspace which perfectly preserves the neighborhood structure in our original space, we will not lose the performance on matching. Fortunately, the GL lemma tells us if we project data to a randomly generated subspace with some proper designs, we can actually preserve the original distance between the points. As you can see from this lemma, if we choose the dimension of projection as k, k is on the order of big O of log n, n is number of samples, we can actually have the bounded pairwise distance in the new space. So by using this GL lemma and also the guidance from this lemma to choose the proper dimension of projection, we can create a number of random projections and easily reduce the dimension of the input data. And after the projection, we can perform the nearest neighbor matching by using a proper distance metric. So this idea is very simple and straightforward. We have some evaluations on synthetic data and real-world data. On this synthetic data set, we created 1,000 samples, and for each sample, we have 200 features. The true outcomes are determined by a set of basis functions, and we also simulated the outcomes by using a normal distribution. After the design, we know that the ground truth of ATT in this case is 1. And based on that, we can use the metric of average of mean square error to measure the performance of different methods. Indeed, we use the 1,000 simulations and compare the average mean square error. This figure shows the comparison between our model, the red curve, and the baselines. So the x-axis shows the number of dimension, and the y-axis shows the mean square error. You can see that because the Ross-based method, the black line, and also the propensity score matching, they have the fixed number of dimensions. So they only have one value to compare with other baselines. And in addition to the random subspace, which is our method, we have 3 baselines on subspace learning, including the PCA, LPP. And as you can see, when the number of dimension is small, our method have much lower mean square error compared with the baselines. Then with a larger number of dimensions, then we assume that the random projection will not perform well according to the lemma. So our method will have a larger mean square error. And it's also interesting to see that the best performance of our method is corresponding to a dimension around 5. And because we have 1,000 samples in this case, the big O of log n is actually around 5, which matches the theoretical result. We also evaluated the performance of our method on real-world data. In this case, we use a marketing data set, which contains the email campaigns and about 2 million customer data set. In this case, the treatment is defined as the two types of promotional emails. And these two types of emails have the same design and the same content. The only difference is the number of discount they provided to customers. And we have about 1.2 million customers in control group and 0.8 million customers in the treated group. For each customer, we have about 200 feature vector, 200 dimensional feature vector. The outcome on the dataset are defined as the open or click the emails. So basically, we want to evaluate whether the promotional email will be effective in terms of the click rate or open rate. Because we don't have ground truth value of causal effect on this dataset, we design the pseudo-treated population from the control group so that the true causal effect on dataset will be 0. And we can still evaluate the performance of different methods on the dataset. As you can see, we have different number of samples and also different outcomes, the click and open. You can see in most cases, our method, the red curve, perform better than the baselines in terms of the mean square error. And interestingly, in some cases, we can have the best performance when the dimension is around 8, because the GL lemma tells us the best dimension for dataset is about log of big N, and N is the number of samples. The next method is informative subspace learning, which introduces the Hilbert-Schmidt independence criterion to nearest neighbor matching. This method actually learns two linear projections for control outcome estimation task and also the treatment outcome estimation task. The method maximizes the nonlinear dependency between the projected subspace and the outcome. This is the loss function. As you can see, the HSIC function has two inputs. The first term is the multiplication of X and M. X indicates the original feature matrix, and M is the projection. So the second part is the factor outcome. And this term want to maximize the dependency between the transformed data set and also the outcome. The second term is the regularization, which penalizes the transformation matrix to avoid trivial solutions. This method has been evaluated on the IHDP dataset, which contains over 700 samples, including about 600 control units and 139 treated units. Each sample has 24 covariates. According to this table, we can observe that the HSI in nearest neighbor matching with HSIC method performs much better than the baselines in many cases. Next, I want to talk about the nonlinear and balanced subspace learning. As we know, the challenges here is how to deal with the increased bias with dimensional data and how to deal with the complex and unbalanced distribution of high dimensional covariates. The random projection method could be useful to reduce dimensional data, but it might not be useful to deal with a complex distribution of data because of the linear projection. And it can also account for the, it cannot account for the unbalanced distribution. So these limitations of the random projection method motivate us to design this solution, which contains 3 parts. The first part is to convert the counterfactual prediction to a multi-class classification problem so that we can use some pseudo labels to help the model training. The second term is ordinal scatter discrepancy criteria, which involves nonlinear representations by kernel mapping. And the third one is maximum mean discrepancy criterion, which can be used to minimize the distance between two groups so that the representation space will be balanced. This is our objective function. The first term indicates the counterfactual classification term, and the P is the projection we want to learn. The phi of X means the kernel mapping by using the kernel function phi. And YC is the outcome. The second term of the loss function indicates the maximum mean discrepancy term. As you can see, this term wants to minimize the distance between the control group and the treated group in the feature space. Although this objective function looks complicated, it has only one variable to optimize, and it has a closed form solution, so the calculation will be very efficient. Again, we evaluated our model on the synthetic dataset and also real-world dataset. On the same synthetic dataset as before, we can see the comparison between our model and the baselines. The blue curve shows that in all the cases, our new method performs better than the random subspace-based method. And on the HDB dataset, we can see the comparison between our model and the other baselines. In terms of the mean error of ATT and the standard deviation, we have a pretty good performance. The next dataset is from a randomized study of job training program, which has about 300 units in the treated group and about 3,000 units in the control group. In this dataset, we have the ground truth value of the treatment effect. And as you can see, compared with the baselines, our method can produce a quite accurate estimation of ATT as well as the standard deviation. The bias of our method is much lower than the baselines. Most recently, we proposed a method to learn the selective and balanced feature space for causal inference. Our motivation is that some variables in dataset may not be relevant to the task. So we want to introduce the feature selection to matching estimators. Therefore, we want to learn a selective and balanced representation space, and we want to learn the feature space by using the deep networks because of the capability of modeling the complex data distributions. As you can see from this figure, we want to rule out the effect of the irrelevant variables, but mainly focus on the other types of variables. This is our framework. Given the input data X, we have a few layers to account for the feature selection, and then after a few hidden layers, we have the bottleneck layer as the new representations. To guide the model training, we have two branches afterwards. The first branch is used to predict the treatment of the sample. And the second branch is used to predict the outcome given the input. After model training, we will use this layer as the new representation space and perform matching in the new space. According to the experiments on different datasets, we can see the benefits of this kind of feature selection and balance the representation space for causal inference. Although in the original IHDB dataset, we don't have a very good performance in terms of the individual treatment effect estimation. For the other cases, especially for the data with some additional noisy features, we can perform much better than the baselines. So we have discussed some subspace learning methods for causal inference. And we know that most of methods in this category, they are highly efficient because of the closed form solution. However, there are still some limitations for these methods. For example, the subspace learning methods, they usually have strong assumptions on the underlying data distributions. And also, they are usually combined with the matching estimators, but they are not capable of estimating the counterfactors directly. Next, Liuyi will introduce how to design deep learning methods for causal inference.